We are studying power series. Usually they converge on some interval. For example, if the radius of convergence is 0, the interval will be truncated, it will be just 1 point. If the radius of convergence is, for example, 2, we would get some interval such as from 0 to 4, that might be possible. If the radius of convergence is infinite, we will get an interval from minus infinity to infinity, that is the whole real line. Well, can we find a formula for R? The trick what we need to do is to use the ratio test. If we have a series consisting of ANs, then ratio test tells that we should consider the fraction of the consecutive terms and take the absolute values and then see if we will have a limit. If the limit exists and is less than 1, then our series will converge. If the limit exists and is larger than 1, then our series will diverge. So let's take our power series and call the general term an. Now an plus 1 divided by an in the absolute values will be looking like this, and we can delete these terms from here. We will have just one term of x minus x0, and we can arrange the thing to be like this. Well, this number here does not depend on n, we can take it out from the limit, and then we can think in that way that we divide by Cn divided by Cn plus 1, that's one way to think about it, and we can shift this fraction to the other side then, and it will go upside down. And now this relation tells that this limit here must be the radius of convergence. So we obtained our formula. Let's see some examples. In the first case, an is equal to n. An plus 1 divided by an. I almost did a mistake. It will be the other way around than in the ratio test. An divided by an plus 1 is n divided by n plus 1. Well, this converges to 1 when n goes to infinity. So we obtain that radius of convergence is 1. So radius of convergence for that series is 1. And the center seems to be 0. So we will get that the series converges on the interval from minus 1 to 1, diverges from minus infinity to minus 1, and in the interval from 1 to infinity. And for the endpoints of these intervals, that means for x equal to 1 or x equal to minus 1, we don't know what happens. Let's then consider this series. An seems to be 1 divided by the factorial of n. An divided by an plus 1 is now 1 over n factorial divided by 1 over n plus 1 factorial. We can rearrange the terms here and cancel out most of the terms. We will get n plus 1. This converges to infinity or approaches infinity as n goes to infinity. So our ratio of convergence is infinity. So n factorial grows so fast that the series will converge for all real numbers x. Now we have a little bit strange series. The ANs seem to form an increasing sequence. Well, let's see. AN divided by AN plus 1 is, what is that? If we separate one of these n plus 1 terms, we can then take the power n as common. Well, it seems it has something to do with the natural base e. We are not yet sure what. The number here inside can be written in the way 1 minus 1 divided by n plus 1. So we obtain something like this. Well, now if we like to have the n plus 1 number, we can arrange it to the power, and we can then put an additional power here, like this. Well, we have that the limit as n goes to infinity from this kind of sequence is e to power x. So that seems to be true now. This term here will tend to e to power minus 1. And this power seems to go to 1. So it seems that our fraction is almost like this kind of number when n is large. Well, this will go to 0, so the limit will be 0. So our radius of convergence is 0. So our series converges only for x equal to 0. Let's have an extra example. Let's have both of the things what we had before. Well, now our fraction would consist of these two terms. And we obtain that this here will be almost like n plus 1, and this one here will be almost like 1 over n plus 1 times e to power minus 1. So now we would obtain that when n is large, this is almost e to power 1. So our radius of convergence is 1 over e. Our series converges on this interval. Let's see still a couple of examples where ANs form a geometric sequence. We want to study this sequence, but here it seems that the power of x is not standard. That's not a problem. We can write this term in the way x to power n times x, and our variable x we can just take out from the series. Now the general term is in the standard form. An divided by an plus 1 is now 2 to power n divided by 2 to power n plus 1. We can cancel out most of the things and we will obtain 1/2. So our radius of convergence is 1/2. We would like to have the radius of convergence for this series, but the power of x is not in the standard form. If we denote x squared to be t, then everything is okay. The radius of convergence for our series is 3. So this series converges if t is in this interval. Well, of course such a t is a non-negative number, so actually in this case half of the interval is not so useful. We can solve that we must have that x is between square root of 3 and minus square root of 3. So because in this series we have this non-standard power, we got that its radius of convergence had to be calculated a little bit more accurately, and it is equal to square root of 3. So here are our examples about the radius of convergence. Let's still have a theorem. Let's assume that we have a power series which has some radius of convergence. If we differentiate the general term, we will obtain this kind of series. If we integrate the general term, we will obtain this kind of series. Let's show that these series have the same radius of convergence. I forgot to write my coefficients in the series. Assume that the radius of convergence of the original series is given by this limit. Let the radius of convergence of the derivative series be r1, and for the other series let the radius of convergence be r2. If we try to calculate what r1 is, we will take these terms from here and consider the limit of their fractions, but the term n does not give anything new because n divided by n by plus 1 will go to 1, and in the similar way here dividing by n plus 1 does not give anything special because also this fraction here will go to 1 when n goes to infinity. Also, I think I should have the absolute values. Well, now I think everything is okay.